Hi, welcome guys. This is an introduction about this lab, the lab number 5, and the keynote rules it relies on the principles of conservation of energy, and this is very useful for analysis and complex electrical circuits. These rules help us to understand how the current voltage behave in different parts of the circuit. In this experiment, we focus on two main concepts: junctions and loops. The junction is a point of circuit where we three or more wires meet. According to the Kinov junction rule, the total current entered in the junction will be equal to the total current leaving. A loop is any closed back within the circuit, and the Kinov loop rule states that the total voltage gain in a loop must equal to the total voltage lost. In the experiment, we measured the current and voltage across the seven resistance and a circuit using the multimeter and sensors. By connecting this data, we can verify whether relationships predicted by this kind of rule are satisfied. We also compare the measurement values and calculate the percent between the theoretical relationships and the experimental results. This will help us to evaluate how the accurate measurements are and understand possible sources of error in the circuit. Thank you.
My name is Jorge Sinceros, and I'm gonna be going over the data for Lab 5. So for Lab 5, we had a circuit that was given to us, and then we had to analyze this circuit and then get our voltage and currents across different resistors. So for the circuit, we have two different parts. We have I1 and I2. In I1, we see R1 in parallel with R2 and R3, which are in series, and we see that R1 is 150 ohms, R2 is 680 ohms, and R3 is 560 ohms. And then we also see R4, which is in I2, we see that as 100 ohms, and then that one is connected to a power supply of 7 volts. So from these values, we were able to calculate our resistance, which we got from actually building the circuit. We got voltage over resistance 1 to be 5.13 volts and current across resistance 1 to be 34.2 milliamps. Now the voltage across resistance 2 is 5.29 volts and the current is 7.78 milliamps. For resistance 3, the voltage is 4.36 volts, the current is 7.78 milliamps. For resistance 4, our voltage is 2.64 and our current is 26.4 milliamps. And also for both of those, we have the source, which is both 7 volts. Now that we have all of our values, we also have our percent error table. So for this, we just had to get our different values. So IR4 is 3.612 milliamps. IR1 plus IR3 is 32.218 milliamps. The VE, which is the same, is 7 volts. Then the VR1 plus VR4 is 6.97 volts. For VR1 is 3.87 volts. For VR2 plus VR3 is 3.88 volts. And from all these values, we have three different equations. And the first equation is IR4 minus IR1 plus IR3 over IR4 times 100%. And that'll give us our percent difference, and with this we got a 0.79% difference. For our equation 2, we got VE minus R1 plus R4 all over VE, the absolute value of that, times 100%. And for that, our percent error was 0.43%. For our third one, we have VR1 minus VR2 plus VR3 over VR1 times 100%, and that gave us a percent difference of 0.25%.
Materials and equipment for Lab 5. In this experiment, we analyzed an electrical circuit using Kirchhoff's rules, which are based on the conservation of energy and conservation of charge. To perform this experiment, several materials and electronic measurement devices are required to reconstruct the circuit and accurately record electrical values. First, we use 4 electrical resistors labeled R1 through 4. Each resistor limits the flow of electricity currents through different paths of the circuit. Before assembling the circuit, each resistor is labeled using small pieces of tape so that they can easily be identified throughout the experiment. The actual resistance value of each resistor is measured using a multimeter to ensure the experimental values match our calculations as closely as possible. Next, we use a power source, specifically a signal generator, set to direct current. The signal generator provides the electrical energy that drives the current through the circuit. For this experiment, the generator is configured to output 7 volts of DC voltage with a voltage limit of 10 volts and a current limit of 1.1 amps. This ensures the circuit operates safely while still producing measurable electrical signals. To measure the electrical behavior of the circuit, we use 2 important sensors, a current sensor and a voltage sensor. The current sensor is inserted directly into the circuit path in order to measure the amount of electricity current flowing through specific resistors. Since current must be measured in series, with the components being studied, the sensor is placed at different points of the circuit depending on which resistor's current is being measured. The voltage sensor is connected in parallel across a resistor to measure the voltage drop across that specific component. Measuring the voltage difference across the resistors allows to verify Kirchhoff's loop rule, which states that the total voltage gained in a loop must equal the total voltage lost. The experiment also uses a digital data acquisition system such as Pasco Capstone software to record the electrical measurements in the software interface. 2 digital displays are configured. One display shows current in milliamperes and the other shows voltage in volts. These readings allow us to observe the electrical values in real time and capture screenshots for documentation in lab reports. Finally, the physical circuit is assembled using connections, wires, and jumper cables connected to the Pasco. Once all materials are prepared, the experiment is processed by assembling the circuit, measuring current and voltage across resistors, and using the collected data to verify Kirchhoff's junction rule and loop rule. Lab procedure. In this experiment, the objective was to construct an electrical circuit and verify Kirchhoff's junction rule and loop rule by measuring current and voltage at different points in the circuit. First, the circuit components were prepared. 4 resistors labeled R1 through R4 were identified and their resistance values were measured using a multimeter. Each resistor was labeled to ensure accurate tracking during the experiment. Next, the circuit was assembled according to the diagram provided in lab instructions. The resistors were connected using wires to form multiple branches and meet at junction points. A direct current signal generator was then connected to the circuit to supply energy. Once the circuit was constructed, measurement sensors were installed. A current sensor was inserted into the circuit in series with the components being tested to measure the flow of current. A voltage sensor was connected in parallel across individual sensors to measure the voltage drop across those components. After the sensors were connected to the Pasco Capstone software we used to monitor and record the data, the current sensor readings were displayed in milliamperes and the voltage sensor readings were displayed in volts. Measurements were taken for each branch of the circuit to be used for final reports. Finally, the collected current and voltage data were analyzed to verify Kirchhoff's rules. The current at junction points were compared to confirm that the total current entering the junction equals the total current leaving the junction. Additionally, the voltage values across each loops were added together to confirm the sum of voltage gains and drops equals 0, demonstrating the conservation of energy in the circuit.
In conclusion, the experiment about to understand verify the Kirchhoff rule in electrical circuit by measuring the current and voltage across the resistors. We are able to test the Kirchhoff rule and the loop rule. The results shows that the sum of the current entering and leaving the Kirchhoff was extremely equal, and the total voltage in the loops also conserved, although the values were not exactly the same. They were very close, which supports the conservation of energy in electrical circuits. The small difference between the theoretical relationships in the measuring values could be caused of several factors, such as measurement error, resistance tolerance, or small variation in power supplies. This is also possible that its connections in the circuit were not perfect. These differences can be minimized by making sure the connections are secure, using the precise measurement instrument, and repairing the measurements to obtain more accurate results. Overall, the experiment confirmed that Kirchhoff rules are effective tools for analyzing complex circuits.
Thank you for watching this week's lab. We have for data and analysis, Jorge. For materials and procedure, Pablo. For video editing, recoding and conclusion, Manuel. For intro and conclusion, Victor. Thank you for watching this week's lab report.